Hello, hi, welcome to Upsana classes. Today in this video, let's learn about the 2-bit comparator. So before that, hard work beats talent when talent doesn't work hard. So let's work hard whether we have talent or not. So see, in comparator, 2-bit comparator, we have A, B, okay. The inputs for the comparator are A, B. But I am telling you about the 2 bits. So for A, I'll have 2 bits and for B, I'll have 2 bits. Regardless of the inputs, any comparator will have only 3 outputs. What are those? A greater than B, A less than B, A equal to B, and A less than B. Right. See, we know that the comparator is a combinational logic circuit, right? To design a combinational logic circuit, we have to follow the 6 steps. What are those? First, we have to analyze the problems. Our analyzation is we are going to design the comparator that is of 2-bit. And then next, we have to determine the number of the inputs and outputs. So we also determined the inputs. What are the inputs that we are going to have in a 2-bit comparator? 4 inputs. 2 for A and 2 for B. Right? 1, 2, 3, 4. 4 inputs and 3 outputs regardless of inputs. Okay. Then we have to name that. We also, that is the third step that we have to follow to design a combinational logic circuit. So that is, I have also named the inputs like this: A1, A0, B1, B0, and the outputs are like this. Fine. Then fourth step, we have to draw the truth table where it define the relation between the inputs and outputs. See, also drawn the truth table. In order to avoid the lagging of the time of the video, I have already drawn previously. So this is the truth table. The inputs and outputs. Fine. How we get the outputs for this? See here, 0, 0, 0, 0. Both are equal, right? So we will have the comparator output A equal to B at high and making all other as low. If you see here, any randomly you can take 0, 1, 0, 0. Here A is higher, greater, right? So we will have at here A greater than B. 1, 0, which is greater 1, right? So A greater than B, like this. So next, step number 5, we have to have a simplified Boolean expression using the Karnaugh maps. So Karnaugh map is the only method that gives the direct step after the truth table. That is a simplified Boolean expression that we can obtain, right? See, I am using here SOP as it is simple to me to write. SOP, that is sum of products. So we don't need any inputs, we need only outputs to have the Karnaugh map, to obtain the simplified Boolean expression. So let's start the inputs. The outputs are these. Okay, fine. I would like to draw first for A greater than B. A greater than B. Okay, here A greater than B, as it is SOP, we will have to consider at the position here, here and here. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 and 15. 0 to 15, total 16. Because we have the inputs as 4. So 2 power n, where 2 power 4 is equal to 16 combination that we obtained here. So those. Okay, fine. SOP. As it is SOP, we have to consider the position 4, 8, 9, 12, 13 and 14. So how to get the cells in the K map? Same, which based upon a relation 2 power n. So as it is a combination of 4 bits, so we have to take 16 cells. Where it should follow the 1-bit change code or gray code. Right. Here I have to have the inputs at this side, here A and B. So for A I have A1 and A0, right? A1 and A0. And for B we have B1, B0. So as it follows the 1-bit change code 0, 0, 0, 1, 1, 1. Not 1, 0. See, only 1 bit is changing, that is 0 here, changing to 1 and 1, 0. Okay. So 0, 0, 0, 1, 1, 1 and 1, 0. Right. So we will get 0, 0, 0, 0. That is 0, 1. Here 0, 0, 1, 1. Which is 3, 3, 2. 0, 1, 2, 3. 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 and 15. See, at 15 position 1, 1, 1, 1. Right. I think you know about the Conov maps all about. So we have the 1 set 1, 4, 8, 9. For A greater than B, I am saying first. A greater than B. So for A greater than B, we have the 1 set 4 and 8. Here 8 is here 8 and 9 and 12 and 13 and 14. So we have to have the maximum grouping in this Conov map. So I have to group here 4, here 2, and if you see here we have 1, but we can group side by side grouping with this bit, right? Side grouping. So as we have 1, 2 and 3 groupings, so we will get the 3 terms in the Conov map. I mean in the equation, Boolean expression. So if you consider this grouping, that is 1, 1, 1, 4 grouping, we have here this 1, 1 and 1, 0. Here we have 1 as a common to both. So we have to consider 1 where the 1 is associated with the 1. Sorry, A1. So we have to take A1. Fine. Here if you go upside, we have 0, 0, 0, 1. We have the common at the 0th position, right? So we have to consider the position of P1 as it is associated with P1. As it is 0, we have to take B1 bar. Why? Because as it is a SOP, sum of products, in sum of products, when we get the zeros, we have to put in a bar. So B1 bar. Okay. See, if you see this grouping 1, 1, you will have here 1 as a common, that is associated with A0 plus A0. If you go upside, we have 0, 0. So we don't have any other term to cancel. So nullify. So we have to take both bit. So as they are 0, zeros, so we have to consider in the bars. So B1 bar, B0 bar. B1 bar, B0 bar. Plus. We have another grouping here, that is side by side grouping with this bit. So we have to consider this 1, 1. No, don't have another bit to cancel. So we have to consider both 1, 1. So as it is 1, 1, we don't need to put any bars. So A1, A0. So if you go upside to these both, we have the common at the zeros position, right? So as these are the least significant bit, that is indicating with the B0. So as it is 0, we have to put in bar. So B0 bar. Okay, fine. Now I have to do for the A equal to B. Same as that. No further complication. This is for A greater than B. Now I would like to take for A equal to B. Same as 16 bits, 16 cells, where we have the groupings higher. We have to consider the inputs are A1, A0. See, we have to take least significant bit, most significant bit. The order we have to take A0, A1. A0, A1 you should not take. You should not reverse. So A1, A0. See here, B1, B0. Okay. So 0, 0, 0, 1, 1, 1, 1, 0. Same gray code. 0, 0, 0, 1, 1, 1, 1, 0. That is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 and 15. Here we have one set, the position 0, fine. And then at the position 5, fine. And then at position 9, at 10, fine. And at the position 15. So we don't have to group here maximum because that's not possible, right? So we have to take single grouping. So here if you see 0, 0, 0, 0. So we have to consider all because we don't have 2 bits to cancel. Okay, 0, 0, as it is 0, we have to put in bars. So B1 bar, B0 bar, same as A1 bar, A0 bar. So we will get as A1 bar, A0 bar, B1 bar, B0 bar plus to this position 0, 1. The same we have to consider. So A1 bar, A0, as it is 1. Okay. So if you see here 0, 1, 0 is for B1 which is bar, B1 bar and B0, so same as B0. So plus. And then next here we don't have zeros here, so we don't need to take any bars. So A1, A0, A1, A0, B1, B0. And then plus. Here if you see here 1, 0, here 1 is associated with A1. So A1 and A0 bar. Here if you see here 1, 0, so B1, B0 bar. So B1, B0 bar. Fine. If you see here, if you simplify, if you take some A1, if you take the common of A1, B1 common and here also A1, B1 as a common, then you will get this as this gate, X NOR gate. So A equal to B will be A0 X NOR B0 into A1 X NOR B1. You simplify. Okay, it's very simple only. I hope you can do that. Okay, then next A greater than B. For A greater than B, the same has to be followed. A greater than B, the same, the 16 cells we have to take. That is here A1, A0, B1, B0, 0, 0, 0, 1, 1, 1, 1, 0. So 0, 0, 0, 1, 1, 1, 1, 0. Here 0, 1, 2, 3, 4, 5, 6, 7. I think you know all these. So 8, 9, 10, 11, 12, 13, 14 and 15. You will ask me like that. If I know really, why will I see your video? See, if you see here 1, 2, 3. 1, 2, 3. If you see here 6, 7. 6 and 7. And then here we have position at 11. 11. The same, we will get the equation as is only. Grouping 4, 2 and 1 we have. The side edge grouping you can do. Okay. For A greater than B, let me write here itself. Here we have to consider this. So 1 at B1 position. So B1. And the side we have the common at 0. So 0, A1 bar, A1 bar plus. If you see this grouping 0, 0, so A1 bar, A0 bar. And upside we have the common at position 1, this least significant bit where it is associated with the B0. So B0 1. Sorry, no need to put any bar. B0. Okay. And this grouping 1, 1. And you have to take both as we don't have anything to cancel. So plus B1, B0. And then if you see this side, we have the common at 0, right? So 0 which is associating to A0. So A0 bar. A naught bar. So these are the three equations that we obtained from the Carnot maps, output of the Carnot maps. So step 5 is completed successfully. So step 5 is completed. That is, we obtained equation for A less than B. In previous I told it is A greater than B, no, A less than B. And then last step, what is the last step? We have to implement using the gates, right? So what are the gates that we have involved here? Let's see. So A1, so A1, A naught, so B1, B naught. So we have gates for, we have to give to not gates too, because we have bars at some positions, right? So we have to use. So if you see here, I'll tell you directly, let you draw, as the space is not organized here. So I'm telling you orally, let you draw. So see, for A greater than B, so A1, B1 bar. So you have to give these both inputs to which gate? AND gate, because AND gate is used for multiplication. So for 3 multiplications, I mean 3 AND gates output, we have to give to OR gate, which is used to add all these 3 terms. And if you see here, we have to give to 2 XNOR gates. If you give XNOR gates inputs as A1, A naught, B naught, A1, B1 to respectively for 2 XNOR gates, then combinedly you have to give those XNOR gate to 1 AND gate, which is used to multiply both these terms, right? If you see here the position, you have to give these 3 to AND gates, and combinedly all you have to give to OR gate for your addition. Okay, fine. Hope you will do this work. Okay, thank you for watching. Please like, share and subscribe.